Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public.
Hi everyone, today we have with us Sherif Abbas, who is a postdoctoral research fellow at the Royal Melbourne Institute of Technology in Australia. Hi Sherif, how are you doing?
Hi, how is it going?
Good. Looking forward to learning about a very interesting science that you have. So let's start with, could you explain your research to us in super simple words, please?
I study how atoms bind together and make very, very interesting and complex structures. So basically, I go bottom up in science, and I do the theoretical aspect of that. So I use laws of chemistry and physics. I would say actually laws of physics in order to understand how systems, how materials have different interesting properties, how the structure, of a certain material can impact those properties, and how materials behave under various conditions such as temperature, voltage, strong magnetic field, and all that stuff. My focus in materials is on very, very thin or very narrow materials. People call them 2D materials or 1D, like two-dimensional materials, one-dimensional materials. And I also study materials with very, very tiny little defects or disorder. And that's a vast study area in material science, where people study what's called point defects, or defects that are as small as a single atom. So that's like broadly what I do in the material science part of my research. I also try to answer many of the questions in material science by using machine learning. So when I use laws of physics to answer questions in material science, I struggle with the fact that solving or using those laws means solving very complex and terribly complex equations, big equations that require supercomputers, for their solution. Machine learning has enabled me in a couple of instances, in a couple of projects, to solve those problems in a matter of seconds on my personal computer. So I've been trying to, foster this direction, do more of the, of my research using machine learning. Yeah, that's basically what I've been doing.
Okay, it's really interesting. So I'm sure you have a lot to tweet about and inform our followers about.
Absolutely,
Which brings me to the next question. It says, what can the followers expect in the week that you will curate the Real Nano Twitter account?
So I'll be talking mainly about the material science I do. So the material science I do is theoretical, and the biggest, let's say the most popular theoretical approach to study material science bottom up, as I said, is density functional theory. I use density functional theory more than any other theoretical approach that I use for studying the sort of things I said at the beginning, like 2D, 1D materials, defects, and all that stuff. So I'll be talking about DFT, density functional theory, why it matters, a little bit of history. It's a theory that got a Nobel Prize, so it's a big deal. And I've been using density functional theory to propose or to discover new materials, discover properties in materials, help experimentalists explain things that they see in the lab. A range of different applications for DFT during my career as a postdoc. So I'll be giving a little bit, a few hints about, or a few glimpses about this, in the first part of of the podcast. In the first part of the week.
The curation, yeah.
And then I'll talk about, okay, DFT is great and all that, but there are many issues in DFT, and we can say that there are many failures, in DFT, failures that have been requiring theoreticians, to collaborate and to come up with solutions to make DFT more robust, more
Mm-hmm.
generic.
Mm-hmm.
DFT still struggles, by the way. It's a lot of the things that the DFT is being used for are not as generic as one would desire. Like you would use DFT for describing properties of chemical compounds, but then
Mm-hmm.
that same DFT you cannot use to describe properties of diamond, for example. So
Mm-hmm.
I'll be giving some insights about this. I've tried myself, to benchmark some of the things, in DFT against experimental, data to make it more accurate and to find an accurate flavor of DFT. So I'll also be giving some, glimpses of this work that I've done. So
Mm-hmm.
that's about the DFT. Next, I'll be talking about machine learning and how machine learning helps DFT. And I've realized that machine learning has been gathering a lot of interest by
Mm-hmm.
people who are doing DFT and doing other sorts of material science, and even experimentalists have been using a lot of machine learning to predict properties and to discover materials. One of the materials or a class of materials that have been gaining a lot of attention for machine learning is MOFs, metal organic frameworks.
Mm-hmm.
I'm doing some work in this area as well, using machine learning, to predict properties like absorption of certain gases of MOFs, and so I'll be talking about this, and also I'm planning to give a short, let's say an hour-long Skype video tutorial, like live video tutorial on using Python, the Python programming language, just very basic, how to use Python for basic machine learning tasks in material science.
Right.
I've done that sort of stuff before, and I found a lot of interest in it. So I'll be doing it again, uh,
Mm-hmm.
using more examples, actual examples, actual work that I've done myself using machine learning and material science.
Mm-hmm.
Yeah, so that's like a very rough outline of what I'll be doing.
Okay,
Yeah,
okay. Yeah, it sounds like a super action-packed week, also with a
thanks.
tutorial probably
Yep.
on Python and machine learning. So it sounds fantastic. Looking forward to having you on Real Scientist Nano. Thank you very much for speaking with me.
Thank you very much for that. Thanks.
Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.